Hello everybody and welcome to week 9 of building scalable distributed systems. In this introductory lecture we're just going to cover some of the materials in the communication section of the class, and this is essentially following on from last week's lecture. Remember, last week we talked about the underlying network infrastructure which is used to communicate between processes in a distributed system. We talked about the network protocols and the stack and how we use abstraction to enable us to send messages both reliably and unreliably across this massive heterogeneous network that makes up the internet. In this module we're going to move up the communication stack a little bit more, basically to the layer that you see as an application programmer. So we'll talk about the communication paradigms that applications utilize when you build them, and what the properties of those communication paradigms are. We'll also talk about data exchange and what options there are for data exchange and what implications those have on the way you build your systems. So in distributed systems, the major differentiator between communication paradigms is whether the communication uses explicit or implicit mechanisms. And we can basically think about all communication mechanisms using these two types. The characteristics of these include, as the slide says, whether they're synchronous or asynchronous, whether the caller knows the identity of the receiver, and how many receivers or callers are involved in the communication, the multiplicity of the communication link. So synchronous and asynchronous are very different communication schemes. In synchronous communications, application A makes a call to application B responds while application A is blocked. It then returns a value to application A, and application A continues. And application B is then free to service another call from application A or another application which wishes to use its services. In asynchronous communications, application A makes a call but continues to do useful work while the invocation to application B is being serviced. And sometimes you'll get a reply which you handle asynchronously. You typically spawn a thread and wait for the reply, and when you get that reply, something wakes up and you process it. But the main difference here, of course, is that the application A doesn't need to block, and hence it can do useful work while the request it sends to application B is being served. So coupling describes how elements communicate and what knowledge they have of each other. So if they have explicit knowledge of each other, then they tend to be more tightly coupled than if they do not have explicit knowledge of each other. So the example here, A calls B, implies that A needs to explicitly know the identity of B, that B is present when the call is made. If B is down, then the call will typically fail because B needs to be there for an explicit communication. A needs to know the syntax of the requested API that B offers, so it needs to know exactly how to call B. And this also implies that if B's interface changes, you add a parameter or you change the return type, then you must also make a change to A. So there's a dependency there. Another type of coupling, as just an aside, is shared data. If we have multiple threads or multiple processes that all share a shared data element on a machine, then if they know the structure of that data, then they are tightly coupled to that data. And if the data structure changes, then all of the threads that operate on that data need to be changed. So this is a very powerful example of tight coupling. You can also think of it extending to a database schema. If you're issuing SQL calls or using some NoSQL API, and the modules explicitly know the structure of the data and rely on the structure of the data, if you change the schema or the description of the data in the database, then all of the modules need to change. That's another example of tight and undesirable coupling. So explicit invocations, also known as a call return style, it's synchronous. The sender sends a request and waits for the response. The sender has explicit knowledge of the receiver. It knows its identity, and it's typically a one-to-one communication. And we've seen examples of this already in the course: socket programming, remote procedure calls, and that example of that is Java's RMI protocol. Let's quickly go over RPC again. And so RPC is a mechanism to make a remote call from a client to a server. The key is that it attempts to make the call look like a local call. So the client essentially looks like it's calling a local method in an object, except a mechanism is injected which takes the client's call. It processes it locally, turns that call into a network request, as you can see down here. After step number 2, the message is sent across the network. At the server side, a stub receives this at the network layer. It knows what the request is. It unpackages the network packets, and it turns them in the server stub into a call, which to the server procedure looks like it's coming from a local object. The server then does its thing, does its work, returns the request, and basically the data just follows, is marshaled, is the right terminology, back to the client. So syntactically it looks like there's a local call being made, but in reality it's a remote call, and it still has all of the implications of making a remote call, such as latencies and the fact that the server may not be alive, or the network may not be alive when you make the call. So examples we've talked about briefly, or will talk about briefly, are Corba, Java's RMI, and the DCE for Distributed Computing Environment, which is really, really old, and I actually wrote a lot of code on in about 1997. So the implications of all this are that the calls are deterministic. Calls happen in the order they're received. You can look at the code and know exactly what order things are occurring in. And you know if the call is processed or not, because the sender waits until it gets a return result or an error. It inhibits scalability because it's synchronous, so the caller has to block until it receives some useful work. It's also point-to-point, so if I'm trying to send a message to multiple receivers using a synchronous mechanism like this, and I have to make multiple point-to-point calls, which can be expensive. It's typically low on overhead, so that's good, but it also creates a syntactic dependency, a coupling between the client and the server. So again, just like we said earlier, if you make a change to the server, you have to make changes to the client, which can be really bad in very large code bases. This exercise today, we're going to look at XML web services, which can be used as an RPC mechanism based on good old XML. So look in the course notes and you'll see an exercise there to work through. Implicit invocation is a slightly different mechanism whereby the sender indirectly invokes the receiver. The sender just sends a message to some sort of address, and it just relies on that message being processed, and maybe it gets a response, maybe it doesn't need a response. Depends on the requirements of the application. But the main thing is it doesn't know who will receive the event and process the event in terms of the identity of the receiver or the location of the receiver. Typically you can implicitly invoke one or more processes, so you can broadcast to a group, or you can just send to say I just want my message to be consumed by a single receiver. And the sender can operate correctly if the receivers are not available. Some buffering mechanism is in place to decouple the sender and the receiver in terms of time. So I can send a message and it may be processed immediately, it may not, depending on the availability of a server. So broadcast is a one-to-many communication. You can actually do broadcast using the IP protocol. There's also a multicast group mechanism in IP, which a lot of technologies are built upon, TIBCO rendezvous being one of them. And basically you send a message to a group, or a topic it's often called, and all of the receivers who have subscribed, who are interested in that topic, receive that message. And the underlying mechanism makes sure that the message gets delivered to all the receivers if it can. There's typically no guarantee that all receivers will receive all events. If the network's down, sometimes the messages won't get through. One higher level mechanism that you'll see for doing one-to-many communications is publish subscribe. As you can see here, the basic elements of publish subscribe, and this is an example based on the Java messaging service, which we'll look at a little bit later, is that you have a messaging server that has something called a topic. It's basically just a named location for messages of a particular type. So publishers publish to the particular topic, and subscribers who are interested in that topic can register with the server and say, if something gets sent to this topic, please send a message to me. So the server receives the message and sends it to all of the subscribers who it believes are active. If one of these is down, it may or may not get the message when it comes back up. There's typically no guarantees of delivery unless you involve higher level mechanisms such as transactional support, which gets tricky with publish subscribe. The implications of publish subscribe is extremely flexible. You can create topics and you can add and remove both publishers and subscribers at runtime. So this enables you to build very flexible systems where things come and go and express their interest in messages. And you're reducing static dependencies. Publishers don't know who the messages are being consumed by, and subscribers typically don't care who they're getting the messages from. It's scalable. You can have multiple elements, and typically you can scale at the server level by having multiple servers handle the load as it grows. The performance is typically pretty good, depending on the server architecture and how well it's built, but it can be difficult to predict loads and latencies because messages are essentially held in topic queues, and under load these queues can get really long and maybe they don't get delivered that quickly. If there's 1,000 messages in a queue already, you have to wait until the first 999 are delivered, and so predicting latencies and measuring latencies can get tricky. When you design these systems, you've got to think about the event model. How do publishers decide what events to publish on, and how do subscribers discover topics that have relevant events? So this has various mechanisms depending on the technology you're using, maybe directory services, or maybe you can have topics that have wildcard names to enable you to receive messages from multiple topics. You also got to think about the design of the broker which you're using. If it's a single server, it can become a bottleneck. Can you scale it out? Can you deploy topics or queues to multiple systems and load balance requests across those? And you'll see as we look at first of all the JMS and then a more sophisticated technology which came out of LinkedIn a little bit later, how scalability really becomes important in the design of the broker. Messaging is just a simpler version of publish subscribe. Essentially you have a message queue which messages are pushed into, sent to, and subscribers, receivers pull them off and process them. Each message typically goes to one receiver, so there can be a pool of receivers just each pulling messages off and sharing the load from a particular queue. You can actually use queues as a send-receive mechanism. So senders can send a message to a queue, and then there can be a reply queue which receivers can use to send responses back to the receivers, again in an asynchronous fashion. All of these mechanisms require you to think about the data exchange formats that you're going to use, and There's obviously a number of typical ones listed on the slide there: text, binary, tab delimited, etc. But very common now are the use of standards such as originally XML, but now much more predominantly you see JSON as a self-describing format for sending messages across brokers. And this is something that you'll get a lot of experience with in the course, certainly JSON. So communications paradigms can have a big performance on the big effect on the scalability and performance of a system, and also on its flexibility, how easy it is to reconfigure, how easy it is to change based on the coupling of the solutions that you decide in your application. So you really need to pay careful attention to the design of the communications paradigms that you use, and think about how this will affect the quality attributes of your system.